Hello everyone, I am B. Shafina Banu, Assistant Professor of Mathematics, Jamal Muhammad College, Trichy. Today the topic is Cauchy theorem in algebra. The statement of the theorem is if P is a prime number and P divides order of G, then G has an element of order P. The condition of this theorem is P is a prime number and P divides the total number of elements of a group G. Then we have to prove G has an element of order P. That is to prove A power P equal to E. So proving this theorem, we have to use the induction methods. That is to prove this theorem by induction on order of G. So assume that it is to be true for all group T such that order of T less than order of G. That means this theorem is true for all group which has less order of G. If for any group W of G, W not equal to G and P divides order of G means then this theorem is true for this group W. That means there exists an element of order P in W and there would be such an element in G also. Suppose P is not a divisor of the order of any proper subgroup of G. This is our assumption for this part. So we already know the proper subgroup definition. That means this is a proper subgroup of G that is not equal to G and the null set. Then only that subgroups are called proper subgroup. So also we know that the result A is not in the center of G if and only if the normal subgroup N of A not equal to G. This is our well-known lemma. Then we know that normal subgroup N of A is a proper subgroup of G, and so by our assumption P doesn't divide the order of N of A. Then we have to use the class equation, that is order of G equal to summation A belongs to G order of G by order of N of A. In this class equation the summation is splitted into two parts. One is A belongs to center of G Z of G and A not belongs to the center of G, that is Z of G. So we have to split this summation into two parts, means then the first summation gives the total number of elements of center of G, that is order of Z of G, plus the second part comes as it is. In this term we have to use the previous lemma N of A not equal to G in the place of A not belongs to Z of G. So since P divides order of G and P does not divides order of N of A, means P divides order of G by order of N of A. That implies P divides summation of order of G by order of N of A. That also implies that P divides order of Z of G. Thus Z of G is a subgroup of G whose order is divisible by P. But we have assumed that P is not a divisor of the order of any proper subgroup of G. So that Z of G cannot be a proper subgroup of G. That implies Z of G equal to G. Thus G is an abelian. Because we already know the result. Z of G equal to G means G is abelian. So that then there exists an element A not equal to E in G such that A power P equal to E. Hence proved the theorem. And finally, thank you.